Today we're going to do test 1 for my Intro to Stats course. If you want to see more videos like this, subscribe and smash the like button. Alright, before we get started, join me in the simultaneous sip. Question 1. For each of the variables below, say whether it is quantitative or categorical, and name an appropriate method to display it. A. Average weight of middle schoolers each year from 1990 to 2020. B. Whether or not you've tested positive for COVID. C. The amount of time you spent studying for this exam. And D. Your home state. So this is pretty straightforward. A is going to be quantitative because it's a number, right? The average weight. And the best way to display it, I would say, is a time plot so we could see how the weight changes by year. For B, whether or not you've tested positive for COVID, that's either going to be yes or no. Those are categories, so it's categorical. And a bar graph or a pie chart would be a perfectly fine way to display these data. C is the amount of time you spent, the amount. That should be a number, so it's quantitative. Hopefully it's a big number. And it seems like a histogram would probably be our best option here. So you can see kind of how many people studied in a certain range of time. And D, your home state. Well, there's 50 to choose from. Each one could be its own category, so it's categorical. And again, a bar graph with the heights being the number from each state, or a pie chart saying the percent from each state. Those are both good options. Question 2. A drug company is testing its newest cold medicine on a group of patients. The side effects suffered by each patient during the drug trial are given in the table below. A. Make a bar graph with these data. And B. Why would you not make a pie chart with these data? So for part A, we want to make a bar graph with these data. We could have the horizontal axis represent each of the side effects. So F, H, N, and L. So for fever, headache, nausea, and lethargy. Notice there's 2 patients that had a fever. So the height of that bar is 2. 5 had a headache. So the H bar will be 5. The N bar will be 3, and the L bar will be 2. And we got to make sure to label our axes. So this bottom axis is our side effect axis, and the vertical axis will be the number of people or the number of patients with each side effect. And so for part B, it asks, why is a pie chart a bad idea to present these data? Well, we're not comparing each of the side effects to each other. A person could have many side effects, or maybe they have 0 side effects. So a pie chart wouldn't be ideal here. Also, it's possible that when we count these percentages, they add up to way over 100%. So you would have to be a little careful when you make your pie chart. So I think it's best to just avoid the pie chart for displaying these data because it's not as good as the bar graph. Question 3. Consider the following box plot. A. Give a range for the upper 75%. B. Would it be better to describe this data set with the mean and standard deviation or the 5-number summary? Briefly explain your choice. From looking at the box plot, it's easy to tell what the range for the upper 75% is. It's starting at the line from the box and it goes all the way to the top. So if we look at the scale on the left, we can conclude that shoe sizes between a size 6 and a size 9 make up the upper 75% of the data here. For part B, it asks, would we rather use the mean and standard deviation or the 5-number summary? Well, if we look at our box plot, we could see that the data is symmetric and it has no outliers. So when you have symmetric data with no outliers, the mean and standard deviation give a much better story, tell a much better story of what's happening with the data. Okay, and so in this case, we're going to use the mean and the standard deviation. Question 4. Sketch a density curve of a distribution that is symmetric and has 4 peaks. Label the approximate location of the median, Q1, and Q3. So we want to sketch a density curve with 4 peaks. So let's draw out the 4 peaks. Make sure that our drawing is relatively symmetric and it looks pretty good. The median splits our region in half, 50% to the left, 50% to the right. Q1 cuts out the bottom quarter, and Q3 cuts out the top quarter. So Q1, M, and Q3 break up our region into 4 sections. Each of these sections have 1/4 of the area, and the total area under the density curve is 1. Question 5. Give an example of a small set of data for which the mean is smaller than the first quartile. What's important to remember for this example is that the mean is greatly affected by outliers. So I just listed out a few 10s, and now let's just have a massive negative number as an entry. Our first quartile we could see is 10. Well, there's the median. Here's Q1. And I'm not even going to compute the mean. I know that it's going to be a negative number because of the size of negative 10,000. So our mean is less than 0. Q1 is equal to 10. It's easy to see that our mean is less than Q1 as desired. Question 6. The lengths of needles from Aleppo pines follow approximately the normal distribution with mean 12 centimeters and standard deviation 1.5 centimeters. A. What range of lengths covers the center 95% of Aleppo pine needles? B. Using table A, what percent of needles are more than 9.75 centimeters long? And C. How short are the smallest 2.5% of needles? So for part A, we could use the 68, 95, 99.7 rule, which in our case, since we care about the center 95% of the data, it says that 95% of the observations will lie within 2 standard deviations of the mean. So here the mean is 12. Let's count out 2 standard deviations. So our upper bound is 15 centimeters, and our lower bound, when we subtract off the standard deviations, is 9 centimeters. Okay, so using that rule, the 68, 95, 99.7 rule, we could conclude that approximately 95% of the needles have a length between 9 centimeters and 15 centimeters. Okay, now for B, what percent of needles are more than 9.75 centimeters long? Let's sketch a picture. 9.75 is a little bit less than the mean, so it's somewhere over there. We want to find the region, well, we want needles that are longer, so we're going to want the region to the right. Find the area of this shaded region, the region to the right of 9.75 centimeters. So what we have to do is find the z-score. So we do that, 9.75 minus the mean over the standard deviation. And we get that z is equal to negative 1.5. So now we'll go to table A, and we'll look for the negative 1.5 number in the table. And we see that it's 0.0668. So we're going to use this to help solve the end of the problem. So using table A, we know the area to the left, right? Table A gives us the area to the left of our number is 0.0668. We want the area to the right. So the way we get that is we do 1 minus our number. Okay, so the percent, well, first we're going to write out the proportion, then we could turn it to a percent. The percent longer than 9.75 is 1 minus 0.0668, which works out to be 0.9332, or 93.32%. Okay, now for part C, we could use our answer from part A to solve this problem easily. So here, again, we know that this middle between 9 and 15 centimeters, that area is 0.95, and our curve is symmetric. So the tail to the left has 0.025, or 2.5%, and similarly the tail to the right. So we could just read off immediately that about 2.5% of our observations are going to be less than 9 centimeters. So 2.5%, I wrote percent twice, of needles are shorter than 9 centimeters. If the number wasn't 2.5%, we would need table A. Question 7. Scientists are studying a newly discovered species of newt. They measured the length in centimeters and weight in grams of each newt caught in a pond. Their average length was 7 centimeters with a standard deviation of 1.9 centimeters, and their average weight was 8 grams with a standard deviation of 0.7 grams. These variables are linearly related with a correlation coefficient of 0.85. A. Find the regression line equation which predicts a newt's weight based on its length. B. A newt was measured to have length of 8 centimeters and weight of 10 grams. What is the residual for this observation? And C. A mutant newt was found drinking from a toxic pond. Its length is 30 centimeters. Briefly explain why we can't use this regression line to approximate the weight of this newt. To find the equation of the regression line, we need x bar. X in this case is going to be length because we're predicting weight based on length. We need the standard deviation of x, which is 1.9. We need y bar, which is the average of the weight, which is 8 grams. We need the standard deviation of y, which is 0.7. And then the last thing we need is r, our correlation coefficient, which is 0.85. This is all the information we need to find the equation of the regression line. So remember, y is equal to r times sy over sx, so 0.7 over 1.9, times the quantity x minus x bar, so x minus 7 plus y bar, which is 8. Let's clean this up a bit. We get y is equal to 0.313 times the quantity x minus 7 plus 8. And this is a fine way to leave it. For B, we want to predict the newt's weight based on its length of 8 centimeters. So y is equal to 0.313, 8 minus 7, that's just 1, plus 8. So we would predict that the newt would weigh about 8.313 grams with that length. But our measured weight was 10. So to find the residual, we subtract 10 minus 8.313. And we see that our observed weight is 1.687 grams heavier than what we predicted. And for part C, why can't we use the regression line when the newt is 30 centimeters long? Well, 30 is way far away from the mean. It is so many standard deviations away from the mean, it would be useless to use the regression line for the prediction. The regression line is really just accurate when you're close to the mean. And here, our value was so much bigger than the mean that the prediction would be nonsense. Question 8. Sketch a scatter plot with the following correlation. Briefly explain your answer. A. R equals 0.9. B. R equals negative 0.4. And C. R equals 0. This one's really straightforward, so let's just start by drawing out a scatter plot. R equals 0.9, so our slope should be positive, and all of the points should nearly lie on a line, right? If it was R equals 1, it would be perfectly on a line. 0.9 means it's close to on a line, but not exactly. So we need a positive slope, nearly linear. Easy enough. B, R equals negative 0.4. So here we're going to have our negative association. So points go down as we move across the horizontal line. And 0.4 is not very strong, so it's going to be, the points are going to be kind of scattered all over the place, but you could still see that negative association. And for C, R equals 0, well, you could either have just a non-linear relation or just a bunch of nonsense. So here I just drew out a bunch of dots that aren't positively or negatively associated. They don't have a linear relation. I call it a jumbled mess. And here, even if it had a correlation, it'd be so close to 0 that it might as well be 0. Make sure to subscribe for more Coffee and Math with Dr. Weselcouch. Don't text and drive. Bye-bye.